This video introduces some MATLAB tools that can be used for the analysis of feedback loops. So feedback, which is covered in Chapter 3, is clearly very important for a first course in control. We need to be able to compute and analyse the closed-loop feedback dynamics, and MATLAB files here facilitate a rapid introduction to that because we can save on tedious pen and paper computations. The basics then, there's a simple feedback loop and you can see the sort of transfer functions that evolve depending on whether you want the input, the output or the error. So we wish to create and analyse these feedback expressions with a variety of choices of M and indeed G. What MATLAB files then have we got to support this analysis? Well, the core examples we're going to look at are these three live scripts here: closed versus open loop, overlay, closed loop transfer functions with feedback, and closed loop offset and poles. Now, you should also note that the earlier files on Laplace transforms, transfer functions and behaviours are a useful foundation for these, so really you should look at those first. And there are also shorter, more focused notes in tutorial week 9, and many of the apps and GUIs also focus on feedback design and analysis, but obviously don't show the underlying code. Now, a reminder, as ever, that the purpose here is not to teach MATLAB, but rather to illustrate quickly where the code is provided. So you can go and look at the code in your own time, self-learn how to use it, and then obviously put your own examples in. Let's look at the code then. So we'll start with this file, closed loop transfer functions with feedback. So the top of the file reminds you about what all the relationships are, the sort of pen and paper stuff and the algebra. So there's all the expressions and the notation that we're going to use. Then section 1 repeats some of that just for clarity, but here you see with a specific example, and then shows here lines 4 to 6. How do I use MATLAB to find these closed loop transfer functions? And you'll see the answers appearing on the right, and you'll notice, for example, GC 12 over S plus 4 matches what you've done on pen and paper. And then you can see here GCU on the right, 3S plus 6 over S plus 14 matches what we've got over here from pen and paper. Example 2, so it's just different numbers, a different G and a different M, shows you the code again. So here's the code in lines 13 to 15. So as ever, just a reminder, you can change these lines. Maybe M wasn't 0.6, it was 0.7, so I've just changed it. Run section, and then the new answer will appear. So section 3 gives again just a different example, a different G and a different M. And then section 4 looks at plotting, but we're going to cover that in one of the other live scripts, so I won't dwell on that now. Okay, so what happens if you want to overlay responses with a number of different compensators, or perhaps different systems? But here we'll do different compensators. So you'll notice what we're doing in section 1 is we're saying, let's assume there's a G, but I want to compare 3 different possible compensators. Now this code's a bit tedious. You could be far more efficient, but it's not so transparent if you're more efficient. So what I've done is I've used numbers like 1 to go with controller M1, 2 to go with controller M2, and 3 to go with controller M3. And you see I've just defined all the different transfer functions here because then it's clear what's going on. So first of all, define all your transfer functions, and you can see on the right the numbers have appeared. And now I can do analysis. P1 for the poles with compensator 1, P2 the poles with compensator 2, P3 the poles with compensator 3. So I can compare and contrast very quickly. I can look at the offsets either as a number or later on as a plot. I can do the step responses. You see here I overlay the step responses. We covered that in the last week's video when we looked at how to use step. And then you've got a nice figure here so you can see how do the step responses differ with the different compensators. And you see the legend here makes it clear which is which, and I've also shown the inputs because that's quite important. Okay, I can, if I want, you can see manage and personalize the plotting of the step responses. So here you see I've got different colors, different line styles and all sorts, and I've done that by extracting all the values from step. There you go, you can see lines 39 to 47 is your example, and then doing the plot statements explicitly below. And I've done the same in section 4, but here with the open loop, closed loop poles. By actually calculating the poles explicitly and controlling the plot statement myself, I can use different colours to represent different systems. Finally then, what about offset? Offset's particularly important, so you might be interested to look at how do I calculate offset. So you'll notice here lines 6 and lines 7 show you two different ways of calculating the offset. And if you look over here on the right, you see I've used bode for one, and that's given me an offset of 20%, or I've done it using coefficients, and that's also given me an offset of 20%. So it's showing two different ways, both of which give the same value. And again, you'll see example 2 is just a different example, different numbers, and as ever, you can change these numbers if you want to. Put your own numbers in, and you'll get your own answers. A bit of a caveat, be careful if you have an integrator because you're expecting the offset to be 0 and some of your numerical calculations might have infinities. So there's some warnings down there. So some conclusions. We've demonstrated some MATLAB files which allow students to develop, construct, compare and analyse closed-loop systems. These files are not intended to be comprehensive, and there's more comprehensive notes in sections 6.4 to 6.10.